Welcome. In this video, we're going to take a look at some more optimization problems. We'll be looking at some geometric applications. So let's go ahead and jump into the first question. So this question says that you have 120 feet of fencing to construct a pen with 4 equal size stalls. If the pen is rectangular and shaped like the one below, what are the dimensions of the pen of the largest area, and what is that area? So we already have kind of a picture to go with our optimization here, and that's really the first thing that we're going to want to do when we're looking at any optimization question in terms of geometry, is to draw a picture, and that's kind of already done for us in this question. So next, we want to consider actually labeling this with the information that we're given. So what we have is we have a constraint on this in terms of our materials. So we have 120 feet of fencing. We really call that a constraint in this problem. What we want to optimize is the area. So we want to find the largest area, and so that's what we're going to be trying to optimize. So let's go ahead and label this and see if we can get really two equations. We're going to have a constraint equation, what materials we have to work with, and then we'll want to consider what we want to optimize, which is the area of this pen. So first thing we could do is just consider kind of the lengths and widths of this pen. Since this is rectangular in nature, we don't know that these are exact squares in terms of the stalls. So what we might want to do is label them with two types of variables. So one way we could do this is with maybe a height for all of the vertical bars, and we'll have maybe W or width for the horizontal bars. So we'll have, in other words, this first pen being a height of H and a width of W. So if I consider really the constraint first, so the constraint equation, we could consider that we have 120 feet of fencing. And that 120 feet of fencing is going to be coming split into the width. Looks like we'll have 8 different lengths of W. We could call that 8W. And then we'll also have, looks like 1, 2, 3, 4, and 5 lengths of H size. So we can add that 5H to that constraint. And if I want to maximize my volume, I want to use all of this material, the 120 feet of fencing, and so we will add those two components together to add to 120. What we want to optimize we usually say that's the optimization function here, is we want to optimize area. So if I consider the area of this whole pen, each of those 4 stalls make up the the whole pen. The area of this structure here, we could say, is going to be, well, it's W times H would be the area of one of these. But here I'm going to have actually 4 different stalls of W times H, or W by H. And so we can say that the area here is going to be 4WH. And that is the quantity I want to actually optimize here, or maximize in this case. So with that, let's use this constraint to be able to optimize my area function here. The area function right now is a function of 2 variables, and to be able to optimize this, I'd like to get it down to a function of a single variable, either W or H, and it doesn't necessarily matter which one you go with. And so I'm going to just choose to solve the constraint equation for one variable, and I'll solve for H. I'm going to solve for H, and I'll get H as a function of the width. And so to do that, let's go ahead and take we can subtract 8w, so we get 120 minus 8w is equal to 5 times h, or we could just say that 120 minus 8w divided by 5 is equal to our height. So this is another way to express that constraint as a function of w. And I can use this expression now to substitute into my optimization function. I want to get the area function here as a function of one variable, and this is going to get it done for us. So we can rewrite this area function. We still have the 4, and we still have w, but I can rewrite h here as this function of w. So this would be 4w times 120 minus 8w divided by 5. This allows us to think about the area only in terms of the width. And so now I could actually go out and solve for, well, what's the width that I need, or the value of w, to actually optimize the area. So let's go ahead and do some simplification first, and then we will consider taking our derivative of our area function here. So we'll do a distribution first. We'll say the area is going to be equal to, we'll multiply 4w in and distribute this. We get 480 times w, and then we'll have minus 4 and 8 give me 32 w squared, and all divided by 5. Now, if you'd like, we can rewrite this a little bit cleaner. If we rewrite this expression without kind of distributing this 5 to both terms, we could rewrite this expression as the area equaling 480 divided by 5. We can divide that to get 96w, and then we can say this is 32 divided by 5 w squared. Just to distribute that 5. It doesn't go in evenly the second term, but looks a little bit better for taking our derivative. So let's go ahead and take our derivative. We'll have a prime as our derivative here. And again, the reason why we're taking a derivative is we'd like to go ahead and see where this function here, this a function, has a maximum value. And we can kind of see that this is going to have another shape of a downward facing parabola. And so we will have a peak point. It's going to happen to be on the vertex, so we can consider that as our maximum. So let's go ahead and take our derivative here. We'll have 96 on one side, and then multiplying by 2, we can bring the 2 down to make a negative 64 divided by 5 times w. This derivative function is a linear function, meaning we're just going to get a single solution, which is to be expected. So let's go ahead and set this equal to 0. Do that in the second column here, and say that 0 is equal to 96 minus 64 over 5 times w. Go ahead and solve this for w. We have 64 over 5 w is equal to 96, and we could multiply here by the reciprocal, 5 over 64. To get our final solution. If we reduce this down, we could put this in our calculator. I think it will come out as a fairly even value. If you wanted to reduce this down, you should end up getting w as 7.5, or you could also represent that as 15 divided by 2. So both of those values would be equivalent to the width here. So we could just use 7.5 here. So in other words, our dimensions here were in feet, so we have the width is going to be 7.5 feet. I'd like to know what the other dimension is, because I do want to eventually find the actual area of the pen. And so we can go ahead and consider the constraint one more time to consider how to find the height here. So if I list out my constraint, that was the height is equal to 120 minus 8 times the width, that would be where my width would go, and then divided by 5. And so we know our width here is equal to 7.5. So we just want to express this. Again, that's coming from that constraint, solve for h. And if we go ahead and solve that for h, we'll find that the height here is actually going to be 12 feet. 12 feet. All right. And just a small calculation here. If we wanted to actually find what is the total area here, we have our two dimensions. We have 7.5 and 12. And we could go ahead and just put that back into the area function. So area, again, was 4 times the width times the height. So we'd have 4 times 7.5 times 12. If we take that all together as a product, we should get, looks like 360 feet squared. And we'll call that as our final area here. So our dimensions would be the width of 7.5, the height of 12 feet, and then we'll have a area total of 360 feet squared. And that completes this first optimization. We have a couple more to take a look at, so let's go ahead and jump into the next example. The next example on the top of our page here is a company is going to produce open-topped boxes with square bases that hold 868 cubic inches. We want to know what dimension should the box be to use the least amount of materials. So first thing we can consider doing, again, is to consider a picture. And then we'll want to label that up and then consider what we're optimizing. So the first thing, let's go ahead and take a moment to draw a little picture. We want an open top box with a square base. That's very important in this question. That'll help us a lot. So let's do our best rendition of a box. And we know that this box is going to have, again, a square base. So we'll try to draw this with a good square base. And if it's not perfect, that's all right. We'll just try to draw this as decently as possible. There we go. So if this is our box, we are told that this box, again, has an open top, so there's nothing on the top here. So we're really just dealing with walls and a base. And so if I consider that as the dimensions, if we have a square base, then I'm thinking that we have maybe some height of the box. We'll call that h. And the dimensions of our base have to be the same, those side lengths. So maybe we call that w as well, the width of the box. Again, the width in the front and the width in the side here are going to be the same. So we have a square base, and again, the height could be whatever height it wants to be. So there's kind of the picture that goes along with the open top box. And again, that would be just kind of maybe a cardboard box that doesn't have a top. But we do have really the four walls and the base to consider. So let's consider first how we would think about the constraint. The constraint is what information they give us. So they give us that our box can hold 868 cubic inches. So 868 cubic inches is going to be the volume of this box. And so when I consider the volume of this box, even if we don't have a top, we'd have the same volume. We'd have a volume of the base area times the height, which we would express here as W squared times H. So that would be the volume of that box, all those dimensions multiplied. The quantity that we want to actually optimize is we want to optimize or minimize, in this case, the materials. We want to have the least amount of materials. So what does that mean for a box here? And let's just imagine this is a cardboard box. Well, that's the least amount of materials would actually be really the surfaces on our boxes. We want to minimize the amount of cardboard itself that we're using. And so that would be really a surface area question. So if I take a look at the surface areas that I'm working with, again, I don't have a top. So I'm thinking about the surfaces would be, well, one of the surfaces, and I'll just call this the area function, the surface areas. And again, this is what we want to optimize. Let's do that optimization function. My area is going to consist of, well, the area of the base, we call that just W squared. That's the area of the base. We only have one of those. And then each of our walls, we have one wall, two walls, three walls, and then the face here is a fourth wall. There's really four walls to the sides, and each of those have dimensions of W times H. So we can add to this 4 times W times H. That would be the vertical surfaces. And that would really give us the whole volume of that open-topped box. Okay, so we've got our constraint, we've got an optimization function. Now we just want to kind of put this information together to be able to, again, minimize the area function. So let's go ahead and jump into trying that. Again, with a constraint, it'd be helpful to solve for one of our variables to get area as a function of only one variable. If we look at the area function here, notice that if I substitute H as a function of W, that'll give us a function of only W. It's a little bit more difficult to do it the other way around since we have multiple factors of W in our area equation. So let's go ahead and see if we can solve for H in the constraint function, and we'll use that substitution to help us simplify. So I'm going to, again, solve for the height, H. That'll leave me with a function of W. So we're going to have really just dividing by W squared, I think, is going to give me H. That would be H is equal to my 868 divided by W squared. W squared. So that's what I'm going to go ahead and use as my substitution. We'll go with the area here. The W squared stays the same. Plus, we'll have 4W, and then H will be 868 divided by W squared. We could go ahead and do a little bit of simplification at this point to clean up our area functions. That would be W squared. If we go ahead and multiply through with our 4 and our w. One of those w's is going to cancel out, and then we'll have to multiply 4 and 868. I think you'll find that this ends up being 3,472. And then we'll still have that, again, that w in the denominator, so we'll divide by the w that's left over. So this is the function that I want to find a minimum for, and I think this does have a good minimum because this is still going to be kind of a quadratic-like function, but not quite, because again we have a w in the denominator, but I think we still are going to be able to find a minimum value here. So let's go ahead and find our derivative function first. Another way we can express this second term here is, again, if we bring that w up to the numerator, we really have w to the negative first power here, and that might be a helpful way to express that when we take its derivative. So let's go ahead and take a derivative a prime. We have 2w for our first term. If we bring down a negative, we'll have negative 3,472 times w to the negative second power. And that would be our derivative sitting right there. Now, if we wanted to set this equal to 0, solve for w, I think that would be our next step in optimizing this. We want to find the value of w that forces this derivative function to be equal to 0. So we could rewrite this, set it equal to 0. We have 0 is going to be equal to, we have 2w, and then minus 3,472, and then we could put this w to the negative 2 back in our denominator function, or denominator. Okay. Now we can just go ahead and see if we can rearrange these terms. Go ahead and try to solve for w the best we can. So if we add our second term over, we could call that a positive 4,472 divided by w squared equal to 2w. We could multiply both sides by w squared. And we would get 3,472 and then 2w cubed. We could also divide both sides by 2 to get our next term, set equal to w cubed. That would end up being 1,736, looks like, is equal to our w cubed. And last but not least, we'll need to take a cube root of both sides to get to the value of w. So we'll take a cube root and a cube root. Another reminder, when we take say a cube root of a value x, another way to express that, especially in your calculator, might be helpful, is to take that to the 1/3 power. Just another reminder for you guys, cube root of x is the same as x to the 1/3 power. So that might be a helpful way to apply it in this case. So on the left side, if we take the cube root of that constant value, we're going to get something very close to 12. So it should be about 12.02 here. And then that'll be equal to our variable w. So that's our width. Again, this width should be in inches, so we can go ahead and maybe label that in there too. So this is inches. There we go. 12.02 inches. We'd like to go ahead and maybe see the other dimension of the box. We do also want to find h, and so we can come back to our constraint. That would be a great place to solve for h. Again, we actually have that expression solved for h already, so we could say that h here is going to be equal to the volume that we started with divided by, again, w squared. So w squared in this case would be approximately 12.02 quantity squared. So this will be an approximate for the height here, and that will come out to about 6.01, and that's again in inches. So practically speaking here, if we used 6 and 12 as our dimensions, that's a little bit easier to measure. In reality, those dimensions would give us a good maximum or a minimum amount of materials. So hopefully pretty practical here as in terms of an application. We want to minimize really the cost overall of our materials, and so that would help with limiting the cost, especially if all the sides here are made of the same material, which would be costing the same. So we'd like to minimize the amount of materials used. All right, so we have one more example with a different geometric shape that we want to consider to finish out. This question says that we have Valspar is considering giving away their new paint samples in small cylindrical cans that can hold 35 cubic inches, and that's about a pint. What would the dimension of the sample paint can be to minimize the amount of materials used? Okay, so another kind of a materials cost expression here. So let's go ahead and jump in and see, again, maybe a picture, and then we'll go to a constraint and optimization function. So let's start with our can. We're going to have some cylindrical can. And so if I look at a cylinder here, I'm going to do kind of a little circle with some height. And this might not be accurate to the final dimensions, but it at least gives us kind of a little bit of a picture to go with our thoughts here. We do know that this cylinder is going to have some height. We'll call that h, kind of a familiar variable for us. And then in this case, our cylinder is going to have a circular base, and we'll have that as a radius r. So cylinder can be described by its radius and its height. I think those are the only variables that we'll have to label here. Now we can consider, well, how would we express the volume? That's what they give us here. That's the 35 inches cubed. We'd say that regular volume, which we would call 35 inches cubed, well, we can express the volume of the cylinder by, again, the area of the base times the height. It's very similar to how we did the box, but now the base is a circular shape. So we could say that the base area would be pi r squared times the height here would just be, again, h. So we know that the constraint here is the volume, which is 35 inches cubed. We call that pi r squared times h. So that would be our constraint. The second thing that we can consider is, what are we actually trying to minimize here? We want to minimize the amount of materials used again. So the amount of materials used, again, has to think about the idea of the actual surface area of the materials. So let's consider how we would think about the surface area of a cylinder. And we'll do another picture for this. So Since we have a cylinder, we can think of really any can is going to have some circular top. It's going to have also a secondary circular top on the base, and if we unravel really and kind of cut the cylinder on its side and unravel this, we'll actually have kind of a rectangular figure that's going to come out, and then another base circle, which is the same size. Let's make those similar in size. Something like, if I can make a circle, something like that. There we go. So we know both of these circles, that's the base and the top of this can, just are circles of radius r. Now the kind of unraveled part, let's consider what the dimensions are with that. Well, one dimension we see here in the volume picture is just going to be h, right? So one of the dimensions is just going to unravel as h. And the other dimension is really what's been unraveled around the circle. That would be really the diameter times pi, or the circumference of the circle. So that would be the circumference or perimeter of the circle. We would call that either twice or the diameter times pi, or with our variables here, we could represent that with 2 times the radius times pi. And again, this is going to be the circumference. Because we're unraveling kind of the perimeter of our circle on that one dimension. So if I consider the areas that are considered here, let's just label these as the areas. The middle area would be 2 times r times pi times h. And then the 2 circles would be just pi r squared with area. So when I consider the areas that are involved here, we can say that area is going to be equal to, well, we'll have 2 circles, 2 times pi r squared, and then we'll have plus 2 times pi times r h. I'll just rearrange those so that the coefficients there are in the front. Okay, so that's looking pretty good. That would be our surface area of our cylinder, and that's what we'd like to again minimize here to finish out. Okay, so looking at the constraint and optimization here, again, this is my optimization function. I can go to work to actually see what the minimum value of capital A is. So to do that, I think we're going to use another substitution technique. It looks like the value that we could probably eliminate in the area equation is that value of h. So I'm going to use that constraint to solve again for the value h to be able to substitute. So just looking at this, I think I can divide both sides of this equation by pi r squared. I'll be left with the h. And again, h here is going to be equal to, looks like 35 divided by pi r squared. So let's go ahead and use that to our advantage. We will go ahead and substitute the values that we need. We'll have 2 pi r squared, that remains, and then we'll have plus 2 pi times r, and then h we have as 35 divided by pi r squared. Okay. Let's go ahead and continue the process. We'll go ahead and do a simplification step here. It looks like we could take and reduce down our R quantities, the pi's will also cancel out to 1, and we'll just be left with 2 times 35 and then divided by R. So we'll rewrite that one time. We have pi, or area equals 2 pi R squared. That doesn't change. We'll have the 2 and the 35 give us 70. And then if I look at R, that's in the denominator right now. So I'm going to kind of do one little step with that. That R, the denominator to the first power, we can actually rewrite here as R to the negative first power. And it's kind of similar how we wrote the W previously. So I'll just go right to that. We'll have R to the negative first power. So here's my area function. We're doing pretty well, so I think we're able now to just consider our derivative function. Let's go ahead and nail that down. We're going to have a prime here for our derivative. So doing a power rule, again, this is with respect to the R variable here. Everything else is constant. We'll have 4 pi times R. So we'll bring that 2 down and raise the R to the 2 minus 1, which is 1. And then we'll have next, we'll bring down the negative 1 again here. We'll have negative 70 and then R to the negative 2. So there's our derivative function. Next, we could consider setting this equal to 0 and again solving for the value of the radius. So if I set this equal to 0, we could say that 0 is equal to 4 pi r minus 70, and again, r to the negative 2, we could write down in the denominator as r squared, just as a quick rewrite there. Now we can go ahead and see where we could add and subtract. We could rewrite this expression as adding 70 divided by 2r, or r squared over to the left. We'd have 70 over r squared is equal to 4 pi r. We can then multiply by r squared on both sides. And we'll receive back just 70 equals 4 pi r cubed. And dividing over some constants here, 4 pi, we can reduce those and we'll be just left with r cubed. So this leaves us with an r cubed equaling 70 divided by 4 pi here. If we go ahead and think about taking a cube root, let's maybe write this one more time and I'll show the cube root. We have r cubed if we want to write it on the left, 70 divided by 4 pi. We take a cube root of both sides. Again, that's the same as the 1/3 power. I'll just represent it like that, because that's likely how you'll put it into your calculator. So raised to the 1/3 power, just like that. We'll get back just our r variable. And that r variable, if we reduce down to maybe 2 significant figures here, would be 3.8 inches approximately. So we can use an approximate symbol. There we go. So 3.8 inches for that radius value. Now, this is not the only dimensions that we would have for our paint can, so let's see if we can find the height of that paint can as well. If we look back up at our constraint, we've already kind of solved for that height in terms of r, and so we'll want to use that one more time. We'll just do that in the corner here. we know that h is going to be equal to 35 divided by, we have pi times r, which is our 3.8 squared. Again, we'll do an approximate symbol here for that one. If we look at that in our calculator, I'm going to confirm this one more time here. You can try this out in your calculator. We'll take our 35 divided by pi times 3.8 quantity squared. Make sure that you have maybe a parenthesis around those two values there as you square in the denominator. It might come out a little bit different with the order of operations there. Make sure those pi and the 3.8 squared is grouped. You should end up getting approximately 0.77, round to 2 decimals here. And that's again in inches for that final dimension. Now, the question is, well, is this answer maybe plausible, that we would have a cylinder with a 3.8-inch radius and then only a height of 0.77? Well, that's an interesting question. I don't necessarily think that would be practical in terms of the actual use of space. It might minimize the amount of materials used, but it might not be helpful in terms of storing. Usually can sizes don't have that relationship between the radius and height, so we'll want to recognize that in this question. But it's an interesting kind of trade-off of, you know, maximizing or minimizing the amount of materials used and actually maximizing maybe the shelf space that we could have. So that would solve this question at least. Again, how practical it is to have a cylinder in this specific shape is another question, but at least we've solved for dimensions that would give us the minimum amount of surface area used for that volume. So thanks for watching these videos. Look forward to taking a look at the next section. We're going to be doing some related rates and some other derivative techniques. So thanks for watching, and I'll see you in the next one.